Sorry, I continue the preparation video. So this is the second part. Then I have this textbook. So we have the component of vector v will be v1, v2, and v3 in 3 dimensions instead of conventional u, v, w. As far as matrix elements are concerned, index notation such as A23 to identify the element in the second row and third column. Second row, let me see. Second row is this. So you have 1, 2, 3. Second row is this. Second row. Column. Third column is 1, 2, 3. Third column. This is third column. So this one. This is A23. Identify the element in the second row and the third column has been in use for some time. The advantage of index notation in conjunction with the summation convention is that we can shorten long mathematical expressions. Consider a system of m equations in n unknowns. So you have this a11 x1, a12 x2, blah blah blah, a1n xn equals c1, a21 x1, a22, blah blah blah, a2n xn equals c2, am1 x1, am2 x2 plus 10 blah 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 plus amn xn equals cm. This system of equations can also be written as this way. So we sum over j is from 1 to n, then that is equal to ci. So I can go from 1 to m, j go from 1 to n. In accordance with the Einstein summation convention, we can further simplify the notation by writing aij xj. So this summation is implicit. So this is hidden. So summation over j is hidden. So then aij xj equals ci. So if you have in the index twice, like if you have jj, so this implies summation. If you have same indices, same symbol twice, that imply summation over that symbol. Yeah. Where summation on the repeated index j is implied here. Here I is called a free index and j is called a dummy index. In dealing with three-dimensional Euclidean space, we have indices ranging from 1 to 3, m equal n equal 3. Whenever an index is repeated once, and only once, the term has to be summed with respect to that index. For this convention to be effective, extreme care must be taken to avoid the occurrence of any index more than twice. As in examples, we have aii equal a11 plus a22 plus a33, Aij, Bij equal Bj, Bij, Aij equal Bji, Aj. The symmetry of an array can be expressed as Aij equal Abi. This is a little bit complicated. So I think in this case we have to have this one. Summation I, summation j. You have two summation. Yeah. So this case, I don't know if there is an explanation. There is no explanation. So explanation is like here, A1J, B1J plus A2J, B2J plus A3J plus B3J. Yeah, and each of them has to be like this. A1, 1, B1, this has to be 1, B1, 1 plus A1, 2, B1, 2 plus A1, 3, B1, 3. And the second term, second one, this one is A2J, 21, B21 plus A22, B22 plus A23, B23, something like this. Last one. Of course, the last one, let me change color to yellow. This one is A31, B31 plus A32, B32 plus A33, B33. This is the meaning for this one, for this meaning. This means like this. This means this one plus this one plus this one plus this one. The symmetry of an array can be expressed as Aij equal Aji. This is called symmetric. If an array is skew symmetric, also called anti-symmetric, Bij equal minus Bji. Okay. An arbitrary array C can be expressed as the sum of symmetric and skew symmetric array. So in any array, C can be decomposed between symmetric part and anti-symmetric part, where Aij equals C parenthesis. Is it called parenthesis? C parenthesis Ij equal 1/2. A is symmetric, right? A is symmetric. 1/2 Cij plus Cji. Bij equal called C angular bracket. Is it angular bracket? Square bracket. square bracket ij is 1/2 Cij minus Cji. The subscript inside the parentheses and square bracket help us to avoid introducing new variable a and b. Okay. There are rare occasions when we would like to suppress the summation convention. Suppose we want to refer to A11, A22, or A33. If we use AII, we get the sum of the three terms. We may underline the repeated index to suppress the summation. So if you call AII underscore, which means A11, A22, or A33, not the sum. When we need to substitute one formula into another, we have to make sure that the dummy indices are distinct. For example, AI equals Cij Bj Bj Ci Dj Dji. Okay, so this I is here. So J is dummy index. J is here, and I is dummy index. So dummy index, we have to use different alphabet for dummy index than the alphabet used to the original to specify the original index. So this is ith element of array A, yeah, which is C. So this is strange. Ci. So this is Ci. So this is Ci, and J is dummy index for implicit summation. Second case is Bj. J is the index to specify the element of array B. Yeah, so the dummy index we use on the left hand side, which is I, has to be distinct from J. A direct substitution for Bj in the first equation shows AI equals Cij Ci Dji where I appears 3 times on the right hand side, violating the summation rule. To avoid this, first we write Bj. For Bj, we use dummy index k. Ck Djk and substitute in the first equation to get AI equals Cij Ck Djk. Yeah, so Cij Djk Ck, where J and K are summation indices or dummy indices, and the free index I appears on both sides. The dummy indices are similar to dummy variables used in integration of functions. Yeah, dummy indices are similar to dummy variables used in integration of functions. Yes. Kronecker delta and permutation symbols. Let me see. Okay, this is okay. Part 2. These two notations are extremely useful in connection with Cartesian coordinate. The Kronecker delta is defined as delta ij Okay, two notations are extremely useful. Okay, one is a Kronecker delta. Kronecker delta is defined as like this. Delta ij equal 1 if I equals j, and delta ij equals 0 if I not equals j. This definition assumes that I and j are explicit integers, such as I equal 1 and j equals 3 and no, and it does not imply delta ii equal 1. It doesn't imply. Anyway, elements of Kronecker delta correspond to the elements of identity matrix I equal delta ij 100, 010, 010, which with this delta ii equals 3. So this is summation index, summation convention. So this means delta ii imply delta 11 plus delta 22 plus delta 33. So this is 3. So the delta ij, delta jk, so this j is the summation. Yeah? J is the summation. So you will have this is j is the summation, right? So delta I 1 delta 1k plus delta I2 delta 2k plus delta I3 delta 3k. Yeah. So if I equal k, one of them is 1. If I equal k, one of them is 1. If I not equal k, none of 0 is 1. So you have this. Delta ij, ajk, so you make a j. So this j goes like 1, 2, 3. And if I so this replaced. So this second j is replaced to I. I think this should be okay. Permutation symbol for alternator is defined as Eijk is 1 if ijk are even permutation of 1 to 3. Eijk equal minus 1 if ijk are odd permutation of 1 to 3. 0 otherwise. From the preceding definition we have epsilon ijk. So this is how many permutations? ij. If you permute ij, you have epsilon ji. Okay. So then if you permute ij, you will have epsilon jki. So even number permutation. Yeah, so then we permute kj and ij. So this is also even number permutation. And these are odd number permutation. Odd number permutation. So, and these are 1. If two indices are same, like ijj, jji, this is 0. Explicitly, we have 1, 2, 3, 2, 3, 1, 3, 1, 2 equal 1. 2, 1, 3, 3 to 1, 1, 3, 2 equal minus 1. Figure 2.1 shows the order of indices for even and odd permutations. Even and odd permutation of integers 1, 2, 2, and 3. So if this is clockwise, it's called clockwise. So this is counterclockwise. So this is counterclockwise. So this is even permutation. If you go to 1, 2, 3, or 2, 3, 1, or 3, 1, 2, these are even permutation of 1, 2, 3. And if you go counterclockwise, which is 1, 3, 2, 2, 1, 3, 3, 2, 1, these are odd permutation of 1 to 3. Using the permutation symbol, we may express the determinant of 3 by 3 matrix A as 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 3, 1, 1, 3, 2, 1, 3, 2, minus 1, 1, 2, 3, 3, 2, 1, 2, 2, 1, 3, 3, minus 1, 3, 2, 2, 3, 1, which is epsilon ijk, A1I, A2, J, A3K, or epsilon ijk, AI1, AJ2, AK3 equal 1/6 epsilon ijk, epsilon LMN, A, ILM, A, JM, AKN. So complicated. We can see the second and third equation as the first row expansion and the first column expansion of the determinant, and the last equation as the sum of all row expansion and all column expansion, which add up to 6 divided by 6. which add up to 3. What do you mean? So this is more like this. This is so let's call this. If we call this 1, 2, 3, we can do 2, 3, 1 is also same. 3, 1, 2 is also same. And minus 2, 1, 3 is same. Minus 1, 3, 2 is same. And minus 3, 2, 1, this is also same. Yeah, so we have 6 variations. So if we put these 6 variations together, we can if we put these 6 variations together, we have this expression. Summation. If we sum these 6, yeah, then we have if we sum these 6, we have this equation. This expression is the sum of these 3. So we divide by 1/6 because we added 6 things. We can also express the determinant in terms of cofactors of the matrix. For 3 by 3 matrix, the cofactor of element AI is the 2 by 2 determinant we obtain by eliminating ith row and jth column and multiplying it by -1 to the power I plus j. Let us denote this cofactor by Aij star. Determinant A is Aij cofactor Aij. No sum on j. So this is like this, right? If you consider determinant A11, A12, A13, A21, A22, A23, A31, A32, A33. So you can pick whatever I See, this is no sum on I. You can choose whatever I. So let's choose this one. So then this means you multiply this. This is the first time. And second one is a cofactor. Cofactor is you eliminate these row and column, so the remaining element is the 2 by 2 matrix, and that's determinant of remaining. This is the cofactor. Then you have to sum over I. Sum over j. So this is the first term, and second term you do this one. Multiply by, this is the remaining element, 2 by 2 matrix. So then the third term is this one. Let me see. Let me use this one. And cofactor is this one. This is a cofactor. Observing that Aij star does not contain Aij itself, recall we eliminated a row and a column. We find Aij equal partial A partial Aij. Partial determinant A, partial derivative of determinant A, partial derivative of Aij. When the inverse of matrix exists, we have Aij inverse is this is a little bit complicated. Inverse of matrix exists. How do you prove this? Aij Ij component of A inverse. Ij component of A inverse is this. I didn't know this. Aij. Anyway, is this correct? Oh, it's complicated. A relation between the permutation symbols and canonical deltas, known as the epsilon E delta identity, is useful in algebraic simplification. Epsilon ijk, epsilon mk is delta im delta jn minus delta in delta jm. From this, when n equals j, we get epsilon ijk emjk equal to delta im. And further, when m equals I, eijk equals 6. I don't know where we prove this. Example, skew symmetry. If Aij is a skew symmetric matrix, solve the system of equation. If Eijk, Ajk is Bi. Use E delta identity to get. Where we use the skew symmetry property ANM equal AMN. Let me see. Do we have any exercise program for this? No exercise. Ah, it seems there is no exercise. Let me see. I don't know if we need exercise for this. Okay, let me stop today. I will continue next time.